All right, welcome back. This is Mr. Clucky here. I'm going to explain the last lab that we did, the phase change lab. So in this lab, if we look at our purpose is, well, what are the effects of the addition of thermal energy on a substance while it's going through a change in state? We're focusing in on phase changes here, all right? And our hypothesis is saying, well, if thermal energy is being added to ice, remember we had water, then the temperature is going to increase, decrease, or stay the same. We're going to circle one of those when the ice is changing state. Remember, we're not grading whether or not our hypotheses are correct or not. So go ahead and we're going to make any choice here. And I'm just going to say it's going to increase, right? We may not know right away. All right. So in this lab, recall, we worked with the beakers. We put it in with ice and water, and we heated it up. Or before we heated it up, we just put the ice and the water together. And then we put the thermometer in there, and our first temperature measurement was just with the ice in the water, and we're just recording the temperature. Once we got that first initial temp, we put it on the hot plate. We cranked it all the way up to the highest setting it would go, and we took temperature measurements each minute. This says for 50 minutes, but we did it until it boiled. And then once it boiled, we went 3 more additional ones. Okay. I'm not going to spell out our data again here. I actually recorded it previously. So we're going to go ahead and look at that real quick. Here is, I'm actually going to move these over real quick. Nobody look. Nobody saw this. All right, let's look at our data over here. All right, so if we look over here, we have our time and we have our temperature. All right, our time, we went from a minute to 18 minutes in this situation, and here's our temperature data in Celsius. Notice how in the beginning, we'll say for the first 6 minutes, did temperature increase very much? And the answer would be no for this question, right? Temperature is barely increasing. We're going from 0 to 1 degree to 1 degree to 2. Right, we're increasing by 1 degree basically these whole first 4 minutes, and then maybe by 3 degrees. So it's starting to increase here. Okay, and then we look at these next 8 minutes here all the way up to 15. Notice how the temperature goes from 15 degrees Celsius all the way up to 95. We had a massive increase in temperature. And at the 15 minutes is where we saw water start to boil. And once it started to boil, notice what temperature did there. Right? Is it increasing very much in these situations? And the answer is no again. Compare that to the very first 3 minutes, all right? The temperature is barely increasing at all, all right? No degrees and then 2 degrees. So looking at this, we can draw a couple of parallels from our data, all right? First thing is we're going to indicate, right? Well, let's think about how long did it take water to boil. And if you look at this, right, water took a long time to boil. It took 15 whole minutes to boil. That's a long time, all right? Remember, to get water to boil, we have to change our state of matter. In this case, we went from a solid all the way to a liquid boiling, all right? And to change state, that takes energy. So thinking about it, which states of matter have the most energy or the most thermal energy? Okay, well, a gas, all right, a gas has the most energy. Okay, a liquid also has, I would maybe say like the middle energy if we compare it between a gas and a solid, has maybe that middle point of energy. And then a solid among the 3 states has the least energy in it. All right, so gases have a lot of energy and solids have very little energy. When we think about going from one state to another, to going from, like, let's say a solid to a liquid or a liquid to a gas, energy, remember, has to be gained or lost. All right, to change states, again, energy must be gained or lost. So let's predict. Well, when would energy need to be gained or absorbed? What situations would that take place in? Think for a second. All right, energy would need to be gained or absorbed whenever we're going from a solid to a liquid to a gas, or a solid to a gas, right? Whenever we need an increase in energy, right? And when we think about, well, where would energy need to be lost, or where would it need to be lost, what situations would that be in? Take a minute to think. And this is going to be exact opposite. So energy is lost when we're going from a gas to a liquid to a solid, or when going from a gas to a solid. All right, so here energy is being absorbed, and in these situations energy is being lost. All right, another word for absorbed would just be gained. all right? Recall that thermal energy is needed to change state, all right? And the thermal energy to change state is much greater than the energy, or much greater than the change in energy needed to increase the temperature, noted here. And we're going to see that in the graph we're going to create over here on the side, all right? So let's look over here at the graph. Notice how we've got this kind of, I would say this line chart where we have this steady or this really little increase, and then it increases rapidly, and then it tapers off again. All right. What we're going to do is we're going to go ahead and we're going to put down where those different phases were at on this graph. Okay. So if we recall, we started out in the beginning with a solid and a liquid, right? We had the solid ice and we had the liquid, and then after a while it changed into a liquid, and then to end it, we had it as a liquid and a gas. All right. So if we look at this graph, take a minute and think about where is the water changing state and how does that correlate with what the temperature is doing. All right, so look at the graph. Think about where are my state changes or my phase changes occurring, and what is temperature doing at that point in time. If we look at our graph, our two phase changes are here at the beginning, right? We're melting. And here at the end, we're evaporating, right? We're going from a liquid to a gas or a solid to a liquid. At those spots, is temperature increasing very much? The answer is no, right? Temperature is rarely increasing. But when it's a liquid, when it is in a single state, right? Notice what temperature does. Temperature is greatly increasing, all right? And the reason this is because in order for particles to move faster, we have to increase kinetic energy. But remember, when we're changing state, right, when we're changing phases, all right, energy, that thermal energy from the hot plate and from the beaker is being absorbed by the particles in order to overcome those attractions or the interactions. And then once they attract or interact, they're being carried away by the next phase change. So here, energy is being absorbed by the solid to make it a liquid. So it doesn't have time, it doesn't have any energy to increase kinetic, right? It's not changing speed, it's just absorbing it to move to a higher phase, right? A higher phase change. Here, we're not changing phase, right? We're in the same phase. So here, of course, right, those particles can increase motion. And then at the very end, notice how, oh, we're changing phase again. So temperature can't increase because all that energy that's going into this system is going in to turn it into a gas. So make a prediction. When all this water has been evaporated, when it's all a gas, is temperature going to increase again? And in this situation, the answer would be yes. Once all the liquid is evaporated and we have it a complete gas, that gas can now increase in temperature. All right? All right, let's go ahead and look at some of these questions here at the end of the lab. Okay, the first question says, where did the energy that was needed to the beaker, or where was the energy that was added to the beaker of ice water come from? All right, looking at this question, all right, temperature or the thermal energy came from a few different sources. The main source, all right, the main source of energy came from obviously the hot plate, right? Energy came from the hot plate, but it also came from a few other places, right? Thermal energy also came from the beaker, all right? So indirectly it came from the hot plate, but then the hot plate gave its energy to the beaker. And conversely, the water, when we had the solid and liquid in there, all right, thermal energy is also coming from the liquid water, right? It's all trying to melt that ice, okay? All right, number 2 says, what happened to the thermal, or what happened to the temperature while the ice was melting and the water was boiling? Well, looking at our graph, what happened to temperature while ice was melting, the water was boiling, right? Melting, boiling. Temperature barely increased. So we can say temperature slowly increased or stayed relatively the same. In our third question, where did the energy that was added to the system go while the ice is melting and the water is boiling? So where is energy going while this is melting and while it's boiling? Well, simply, what's going on, right? It's changing phases. So to answer this question, we're going to say energy went to overcome the attractions between particles, and then it was carried away by those particles when it was transitioning states. Right? If we look at this graph here, the energy that went in to make this liquid a gas, all right, all went into the water to make it a gas, and then the gas leaves, right? It's no longer in the system, so it leaves, right? The energy is gone. None of it can be used for kinetic energy. Here, all the energy is going in to change that solid to a liquid. So the solid water particles have no energy to increase in temperature, right? It's being all carried away as liquid. The last question says, suppose you have 2 glasses of water. One contains a small amount of ice, and the other contains a large amount of ice. After that ice melts, will they be at the same temperature? Why or why not? Well, simply, the answer should be no. All right? No, they should not be at the same temperature. And explaining this is a little tricky, so you'll want to make sure you pay attention here. All right? So ice is water that is at 0 degrees Celsius. Okay? That is when water is in the solid state. All right? And water melts, or ice melts, all right, because that liquid is transferring thermal energy to the ice, all right? And this causes it, right? This causes the particles in it to speed up. Okay, but not only to speed up, but also change state, right? They're speeding up and changing state, like in our graph. In addition, we would say that the water wants to reach thermal equilibrium. Wants to reach thermal equilibrium. When we think about a lot of ice versus a little bit of ice, all right, is more energy needed to heat up a lot of ice, all right? Is more energy needed to heat up a lot of ice or a little ice? Right? If you have trouble answering that question, think about this. If I put a cup of water out on my table, what's going to turn into liquid faster? Right? A giant cup of ice or just 2 ice cubes? Thinking about that, right? The 2 ice cubes are going to melt a lot quicker than a whole cup of ice, right? A whole cup of ice needs a lot of thermal energy to melt all of it. So similarly, if we have 2 cups, one with a small amount of ice and one with a large amount of ice in it with water, right? The one with a large amount of ice needs much more energy to heat up and turn that all into liquid. All right? So more energy is needed to melt ice if there is a lot versus a little. All right? Causing thermal equilibrium to shift downwards. So in summary, they won't be at the same temperature. All right? All right. A cup with a lot of water, not a lot of water, but a lot of ice, will be colder after it melts than a cup with a little ice. If you have trouble thinking about this, would you rather have a cup or have a glass of water with 1 ice cube or 10 ice cubes? What's going to keep it colder longer? Obviously the one with 10 ice cubes. So that's a more practical situation in which, right, none of us ever put 1 single ice cube in our soda, right? We always put a lot of ice in there because we want it to stay cold. All right, if you want it to heat up real quick, sure, put 1 ice cube in there. But I doubt on a hot summer day many of us would want our liquid to be warm, right? This is the conclusion of our thermal energy lab. All right, and that's the last video. Thank you very much, and you are free to do the rest of your reviewing now. All right, thank you.